Today we will discuss very interesting concept in probability called Chebyshev's inequality. But before we start Chebyshev's inequality, let us understand the problem that we are trying to solve. So if you know that your data x or a random variable x is Gaussian distributed, distributed, we already know the 68, 95 and 99.7 rule. This we already know. Let's understand what this rule exactly say. For example, let us say the random variable x represents the heights of a students in a college. Students, correct? If we know that the heights are Gaussian distributed, that is, if this random variable x, which represents the height, is Gaussian, or you can say normally distributed, having a mean and a standard deviation, then here there are three things. First thing is that this is a normal distributed or Gaussian distributed, and the second thing is that I know mean, and third thing is that I know the standard deviation. So this is first, this is second, and this is my third thing. If I know all these things, then the probability that my x lies between mu minus 2 sigma and mu plus 2 sigma is 95%. We know this. What it means? Let us say our mean height is 150 centimeter and the standard deviation is, let's suppose, 10 centimeter. Now, because I know that this is Gaussian distributed with some mean and some standard deviation, then what I can say? I can say that 95% of students' height lie in the interval 130 centimeter and 170 centimeter. This comes from mu minus 2 sigma and mu plus 2 sigma. My mu is 150 centimeter. So this comes out to be 150 minus 2 sigma. So 150 minus 2 into 10 comes out to be 130, and 150 plus 2 sigma, 2 into 10 comes out to be 170. So I know that my height, 95% of the students' height lie between these interval 130 centimeter and 170 centimeter. Let me draw a Gaussian distribution for you. So if you look at this Gaussian distribution that I have just drawn, 99.7% of my data lies between mu minus 3 sigma and mu plus 3 sigma. This is my Gaussian distribution. Gaussian distribution has this property that 68% of the data lies between +1 standard deviation and -1 standard deviation. So this is in the 1 standard deviation range. And this is in the second standard deviation, or you can say 2 standard deviation range. And this is in the 3 standard deviation range. That means around the mean, what I mean to say, around this mean, 99.7% of the data lies around this mean. Let's suppose if this is my distribution, Gaussian distribution, and let us assume this is my mean, and let us assume this is mu minus 3 standard deviation and this is mu plus 3 standard deviation. So I know from the simple rule that 99.7% of my data lies between 3 standard deviation range. 95% of my data lies between 2 standard deviation range, and 68% of the data lies within 1 standard deviation range. Now comes the very important question. What if I do not know the distribution? What if I do not know the distribution? What if I do not know the distribution, but let us assume we know the mean, which is mu, and we know the standard deviation. We also know that my mean is finite, and my standard deviation is non-zero and finite. Non-zero and finite. We know these three things. First thing is, I do not know the distribution, whether the distribution is a Gaussian distribution, log normal distribution, or some other distribution. We don't know, but we know the mean, which is finite, and we know the standard deviation, which is non-zero and finite. Now, can I say, let me write this 3 points. First point is, can I say X% of data lies within mu minus 2 sigma and mu plus 2 sigma? Or can I say my Y% of data lies within mu minus 1.5 sigma and mu plus 1.5 sigma? Or can I say Z% of data lies within mu minus 1 sigma and mu plus 1 sigma? This is very important. Can I find these X%, Y% and Z% is here? Here, remember, in the case of Gaussian distribution, we know the distribution already, and we know mean and standard deviation. And hence, we are able to apply this 68, 95, 99.7 rule. But what if I do not know the distribution, but I know the mean is finite and the standard deviation is non-zero and finite? Now, can I find the percentage of points lie within the 2 standard deviation range, that is my X percentage, or 1 standard deviation range, which is my Z percentage, or 1.5 standard deviation range, which is my Y%? Now, you might wonder, what is the use of all these things? Let me give you an example so that you can connect with how this is useful in the real world of data analysis. So imagine you have salaries of individuals in a country. Individuals in a country. And you don't know the distribution of the salary of each individual. Very important thing is that I don't know the distribution. I don't know the distribution. But let us assume you do know the mu and the standard deviation. And also I know this mu, that is my mu is my mean and my standard deviation. Correct? Let us suppose X is a random variable. X is a continuous random variable that represents the salaries of individuals in a country. Now, I can compute the mean using central limit theorem or using some other methods that we have discussed previously, like bootstrapping and things like that. Now, if I know the mean and standard deviation, let us assume my mean is $40,000 and my standard deviation is, let's say, $10,000. $10K. So can I say what percentage of individuals have a salary in the range of $20,000 and $60,000. Let's suppose this is dollar. Can I say this? Or Can I say what percentage of individuals have a salary in the range of $10,000 and $70,000? Can I say this? This is my mu minus 2 sigma and mu plus 2 sigma. And this is my mu minus 3 sigma and mu plus 3 sigma. If my salaries was Gaussian distributed, life would have been very simple. If my salaries were Gaussian distributed, I can say that 68% of my income lies within the 1 standard deviation range, 95% of the income lie within the 2 standard deviation range, and 99.7% lies within the 3 standard deviation range. But here, I do not know the distribution. Now, what do I do? Here comes the Chebyshev's inequality. Very interesting idea. First, let me write what is Chebyshev's inequality, and then we will see how it is useful. Now, here I am writing the formulation. So, if x is a random variable with finite mean, which is mu, and non-zero, and finite standard deviation, which is sigma, and I don't know the distribution. This is very important. I don't know the distribution. Then the probability that the absolute value of x minus mu lies between k sigma is less than equal to 1 by k square. This is what Chebyshev's inequality states. Now, let us understand this. Here I have plotted a distribution to make you understand this thing. So now let us understand this. This basically means that we are k standard deviation away, and here I have k here as a constant. So let's say if I want 2 standard deviation away, then I will put k is equal to 2 here. So this will be 1 by 2 square. So this part and this part is clear. So now what about this part? What this whole thing mean? Can I write it more simply? One thing that you should understand is this Chebyshev's inequality that I have written is going to work for any distribution with a finite mean and non-zero and finite standard deviation. Let's suppose if the distribution is, this is going to work for any distribution. Even if the distribution is normal or Gaussian distribution, this thing will work. So let's say I have plotted a Gaussian distribution here. So let me first write this Chebyshev's inequality in a more simpler form. This is a bit difficult to understand, but you will find this in most of the textbooks and at most of the places in the internet. But I somehow do not like this. So let me simplify this to make you better understand. And then I will make you understand with the help of this Gaussian distribution. Instead, this Gaussian distributed graph. This absolute value of x minus mu is greater than equal to k sigma. So can I write x minus mu is greater than equal to k sigma? This is simple mathematics, which means x is greater than equal to mu plus k sigma. Similarly, I can write this as or x minus mu less than equal to minus k sigma, which implies x is less than equal to mu minus k sigma. So I can write this as probability of x greater than equal to mu plus k sigma, or x is less than equal to mu minus k sigma, which is less than equal to 1 by k square. So in a more simpler form, I can write this as probability of mu minus k sigma less than x less than mu plus k sigma, which is greater than 1 minus 1 by greater than equal to 1 minus 1 by k square. You can observe that this thing is in the k sigma range and mu. This thing is in the k sigma range and mu. Fine. This simply means that if you observe this Gaussian distribution with the help of this thing, you can see that this mu minus k sigma, I'm telling my k, where is my x lies? X is lying between mu minus 2 sigma. That means in this range is greater than 1 minus k square. Or you can say mu plus k sigma, this range, this thing, and mu minus k sigma is less than equal to 1 by k square. So this is one thing that most of the students are often confused. So they are confused at how I arrive from this formula to simply this. This is a major confusion between the students, how I arrive from this thing to this thing. So I will just explain you this quickly. So we have written this probability of x greater than equal to mu plus k sigma, or x less than equal to mu minus k sigma is less than equal to 1 by k square. That means the probability of this thing is less than equal to 1 by k square. So let's call this equation 1. So I'm making you understand how I reached from this formula to this formula. Now let's write the second equation. And what is my second equation? This is my probability of mu minus k sigma less than x less than mu plus k sigma is greater than 1 minus 1 by k square. Let's call this equation 2. So let's understand how I have gone from this to this. So some of you are confused how I have made this jump, right? So let me elaborate and simply explain it to you. Fine. So let's assume this is my random variable x. This is my continuous random variable. I can say continuous random variable. Fine. And let's assume this is my mu, which is my mean, and this is my mu minus k sigma, and this is, let's suppose, mu plus k sigma. Since I assume my x is a continuous random variable, that means it can take value from minus infinity to plus infinity. Correct? Now, what is the first probability saying? The first probability is saying the probability of the values falling in, let's suppose, in this region. In this region, I'm talking about this region, mu minus k sigma, which means this whole region, that is minus infinity to mu minus k sigma. Here, x is greater than mu plus k sigma. That means this region, this whole region, if I circle this whole region, which is plus infinity to mu plus k sigma. Fine. So this region plus this region, probability of this region and the probability, this whole region and this whole region is less than 1 by k square. That's what it is saying. So in other words, you can say the probability that your random variable x lies from the value towards minus infinity, from here towards this minus infinity, this whole region, or your probability that x is greater than equal to mu plus k sigma, which means this whole region till plus infinity, this probability, this whole region probability and this whole region probability is less than equal to 1 by k square. This is my first equation. Now, what happens to the probability of x lying in this region, this middle region, in between mu minus k sigma and mu plus k sigma? What I mean to say, this region, this region. Let's assume this just for simplicity. If the probability of x lying in this region plus the probability of x lying in this region is, let's suppose it is 0.2. Then what is the probability of x lying in this region? This will be 1 minus 0.2. This reason and this are called mutually exclusive events, which is a mathematical way of saying that x can either lie in this interval, this plus this interval, or this interval. X can lie in the interval. X may not lie outside of this interval because there are only two options. X can't lie elsewhere because x lies between minus infinity to mu minus k sigma, or x can be greater than this, or this is one possibility. This is my possibility one of lying in this region or this region. This is my first possibility, and this is my second possibility that x may lie between mu minus k sigma and mu plus k sigma. This is how I am arriving at this thing. What is my first equation? My first equation is probability of x greater than mu plus k sigma, this region, or mu minus k sigma, this region, this whole region, this region plus this region is less than equal to 1 minus k sigma. So what is the probability of x lying between this region? Between this region and this region should be 1 minus k square. Here I have written 1 minus 0.2 because this probability plus this probability is 0.2. So this probability should be 1 minus 0.2. At least it should be 1 minus 0.2. This is not exact. This is at least, because this is less than. This is less than. So that's why this should be at least this thing. It can be greater also. Now, keeping these things that we have just understood, we can write this thing as probability of mu minus k sigma less than x less than mu plus k sigma. That is, I am writing here this reason. This should be 1 minus this probability of x lying between in this region and this region that I want to write. So I can write it as is equal to 1 minus probability of x greater than equal to mu plus k sigma, or x less than equal to mu minus k sigma. I hope you have understood this. This is the same thing that we have discussed here. This whole thing. This probability is equal to 1 minus this probability plus this probability. Look at this carefully. So this thing is one probability. This whole thing is one probability. And this whole thing is one probability. So this is just for understanding purpose. Let's call this as A. And let's call this whole thing as B. Fine. This is just for simplicity. So here we have, I'm writing this whole thing as A is equal to 1 minus, we know that B is less than equal to 1 by k square. We know this. This we know. From where we know this thing? We know this. We know from here. If you look, we know this thing is less than equal to 1 by k square. Correct? So can I write this as A is greater than 1 minus 1 by k square. Why I'm writing this? Because B is anyway less than this thing. If B is less than this thing, then this should be greater than 1 minus k, 1 by k square. Fine. Let's say if I write 1 by k square is equal to 0.1. So what I mean to say, B is less than equal to 0.1. That is 1 by k square. Fine. That means we can say A is equal to 1 minus B. Or in other words, we can say A is greater than 0.9 is greater than 1 minus 1 by k square. I hope you understood this, how this I have arrived from this thing to this thing. So this is easier to remember and understand. This is a little bit complex thing, but you will find this in most of the textbooks and on the internet, but you can use this thing if you want. Having understood this, now let's come to the our first question. What was my first question? My first question was, what percentage of people, what percentage of people salaries lie between, let's say, 20K and 60K. Fine. This was my first question. So let's suppose mu is equal to 40K and sigma is equal to 10K. Let's suppose, just for the sake of understanding. So here, if mu is equal to 20K and sigma is equal to 20K, and I want to understand this thing, this question, what percentage of my salaries lie between, of the people's salary lie between 20K and 60K. So from this, you can say that 20K is equal to mu minus 2 sigma and 40K is equal to mu, and you can say 60K is equal to mu plus 2 sigma, because this is mu minus 2 sigma, let's suppose, and this is mu plus 2 sigma. So probability of 20K less than x less than 60K is greater than 1 minus 1 by k square. Is here k is 2. So 2, because we are talking about 2 standard deviation effect. So this should be greater than 0.75. So the probability that my salaries lies between 20K and 60K is greater than 1 minus 1 by 2 square, because k here equals to 2. So how many individuals salary lie between 20K and the probability is greater than 75%. So at least 75% of the people's salary lies between this region. So I'm talking about at least. That means it could be more. So if salaries, let's suppose if my salaries was Gaussian distributed, imagine if salaries was Gaussian distributed, it would have been 95% of salary lie between minus 2 standard deviation and plus 2 standard deviation. This is why we are not saying X percent of salaries lies between this interval, this region. All we are saying here is greater than 75%. All here we are saying is greater than 75%. The exact value depends on the distribution. I cannot say what the exact value is. If it is Gaussian distributed, it is 95%, which is again greater than 75%. Correct? Similarly, third standard deviation range, this is again 40 minus 3 into 10, 3 sigma, and 40 plus 3 into 10, 40 plus 3 sigma. This is my 40 minus, this is my 10, and this is my 30, 70. So this is greater than 1 minus 1 by 3 square, which is 1 by 1 minus 9, which is 8 by 9. So this is my probability that my salary lies between 10K and 70K is again greater than this percentage, 8 by 9, which is roughly around 90%. So this is greater than 90%. And we know that 99.7% of people's salaries would have fallen in this range. We know that 99.7% of people's salary would have fallen in this range. So this is greater than, that is, at least it is 90%, but it could be greater. But if you do not know the Gaussian distribution, you are guaranteed that greater than this percentage is the people's salary whose lie in this interval, that is 3 standard deviation interval. So this Chebyshev's inequality from an applied standpoint, if you are given random variable for which you know the mean and standard deviation, and you know that the mean is finite and your standard deviation is finite and non-zero, you can answer questions like this. That is one of the biggest application of Chebyshev's inequality in practice. What it literally says is, what is the minimum percentage points that will lie within k standard deviation around the mean? This can answer a lot of interesting questions, as we have seen in this simple salaries example. So hope you have understood this. If you have any doubts or queries, you can definitely comment in the videos. I will happy to respond your doubts. And if you have any further queries, you can definitely put it in the comments. And next, I will keep coming with the new episodes of statistics for AI and data science. Keep learning, keep smiling. See you in the next episode. Till then, take care. Bye-bye. Thanks for coming.